Welcome to Lesson 89. We skipped some, so be careful here. We're following our tales of quadratic functions today with identifying certain characteristics that are going to become very useful in dealing with these things called quadratic functions. So, as far as these quadratic functions go, they have some things you need to understand. Remember that they take the graph as the shape of a parabola, right? And the parabola has one point called the vertex point, where it is the turning point of the parabola. Reaches its lowest, then it turns and goes up higher again. That's called the vertex point, all right? When the parabola opens upward, that vertex point is called the minimum. In other words, it is the least possible value that is on the graph for that particular parabola, all right? The turning point. If we take this and create a parabola that is downward, now instead of a minimum, this vertex becomes the maximum, the highest possible value that could be found on the graph of that equation or that function. Minimum, lowest point, maximum, highest point, and you do that by looking at where the turning point is, called the vertex. Right? We have part of your assignment will be to actually find the minimum or maximum, which you can see is simply done by looking at the thing. You have a graph of a particular parabola, and that graph you look at and you see where the turning point is, where the vertex is, and you see that the vertex here is at y equals 2. Y equals 2, and the point 0, 2 is the ordered pair for that vertex. However, we say that the minimum or the maximum is the value of y at that particular place. So you would say that for this particular parabola, the minimum, because that's the lowest value, is equal to 2 on the y-axis there. Y equals 2. All right? And again, if this were turned around, now you would be finding the maximum, except these would become negative numbers, and the maximum now would be minus 2. The reason for doing this is to understand the domain and the range. You may recall that the domain of a function are all acceptable x values, and the range of a function are all the acceptable y values. If we look at this particular parabola, we see that the x values on the x-axis here, all right, extend to all real numbers, off into infinity. So we would say the domain of this function is all real numbers. However, for y value, the range says that it cannot be above the maximum here. In other words, the range says that for this to be on the graph of this particular function, it would have to be minus 2 or less. So we would say that the domain is equal to all real numbers, and the range is equal to y is less than or equal to minus 2. Everything below minus 2 is considered the range. So here we bring in domain and range into the idea of what's acceptable, what's going to fit, what's going to be on this graph called the parabola. Right? And so the minimum and the maximum help us to do that. Right? So again, if we were to do it this way, we would see again that the domain, all possible x values, go off into infinity in both directions, and our test again is, where does it hit the x-axis? And it hits everywhere on the x-axis. So the domain is all real numbers. The range, however, is where does it hit the y-axis? And we see that below minus 2 in this case, all right, now we're positive again. So below 2, there are no values that fit on this curve. And so in this case, we say the range is everything that is 2 or more. Domain and range. All right? That's one characteristic of parabolas. All right? Another one that's going to come in very handy is this idea of finding what are called zeros. Zeros are where y equals 0, is one way to think about it. Or where does this parabola cross the x-axis? Because everywhere on the x-axis, y equals 0. And in other words, when we talk about finding zeros, we are talking about where does the parabola intercept the x-axis. Some parabolas will have 2 zeros, here and here, for example. Other parabolas might just have 1 zero touching the x-axis in one place. And other parabolas may have no zeros at all if they don't hit the x-axis. So you can have 2 zeros, 1 zero, or no zeros. And when it asks you to find zeros, basically all you have to do is look at where on the parabola it hits the x-axis. All right. So if you're asked to find the zeros here, we have 1, 2, 3. So here x equals 3, and here 1, 2, minus 3, and this 0 would be x equals minus 3. So we would say the zeros for this parabola are 3 and minus 3. All right. This is also where the equation y equals the quadratic is when y is equal to 0. So later on we'll be able to solve for zeros, but for now you just have to look at it, understanding that if it hits 2 places on the x-axis, there are 2 zeros. If it touches the x-axis at its maximum or minimum, there's 1 zero, and the parabola may not touch the x-axis at all, in which case there are no zeros. So zeros, a second characteristic that we need to deal with. All right? And finally, parabolas can be described by what is called the axis of symmetry. In other words, parabolas are symmetric. They have a dividing line, and if you fold it on that dividing line, the graph is going to match exactly. That dividing line is called the axis of symmetry. And when you have a parabola, there is one value for x, where it hits that x-axis there, that divides that parabola exactly symmetrically in half. And that is the x, or that is the axis of symmetry. Now, in many cases, you can be given the graph of a parabola, and you just look at where is the vertex point. That is the key, because the axis of symmetry must always go through the vertex point. That's your clue. You find the vertex, the value of x for that vertex, and you can see that, and that is your axis of symmetry, where x in this case at the vertex is 3.5. And that gives you a value, a dotted line here, where everywhere on this dotted line x is 3.5. And that's called your axis of symmetry, because on both sides of this dotted line, the values are exactly mirror images of each other. All right, they will, be able to do that. Now, here's another interesting thing about the axis of symmetry. All right, is that if you know the zeros and you find the exact average of the zeros, that will give you your axis of symmetry. Notice that in this parabola, the zeros here are 1 and 6. It crosses the x-axis at 1 and it crosses the x-axis at 6. You can find the axis of symmetry value by finding the average of those two numbers. 1 plus 6 divided by 2 gives you exactly in the middle, 3.5. So sometimes you can tell on a graph very easily it is exactly on a particular line and you know where it is, but if it's in between markings on your graph, then you find two values that are opposite each other, like the zeros, and find their average, and that will give you the axis of symmetry. On the other hand, and that's what you would use if you're given the graph of the parabola. But you can also find the axis of symmetry, which will help you in the next lesson to graph things, by looking and finding the axis of symmetry by looking at the equation. All right? And that equation, all right, is the idea of using the axis of symmetry formula. The axis of symmetry formula, which is simply x is equal to the opposite of whatever b is divided by 2a. Now remember that in standard form, a was what the number was in front of the squared term, b was the number in front of the linear term. So the idea is that if you have an equation that you're asked to find the axis of symmetry from an equation instead of a graph. So for example, you're given y equals minus x squared plus 6x plus 5. We see that a is equal to minus 1, right here, the number in front of the squared term, a. B is equal to 6, the number in front of the linear term. And the axis of symmetry formula, right here, x, the value on the x-axis there, that's going to be the axis of symmetry, says that we substitute in b. So we take the opposite of b, minus 6, over 2 times a. In this case, a is minus 1. And we simplify that. Minus 6 over minus 2 says that the axis of symmetry for this particular parabola is going to go right through x equals 3. This little formula here is going to come in very, very handy later on. So make sure you understand it, make sure you can use it. And to help you with that, task number 2 is simply lesson 89, do A through J. All right? Thank you.
Hold on.